NASA has sent spacecraft to every planet in our solar system. Voyager 1 crossed into interstellar space. New Horizons flew past Pluto and captured images of the most distant object humanity has ever visited up close. But there's a region that begins just beyond these achievements, a vast cosmic shell that marks the true edge of our solar system, that remains completely beyond our reach. The Oort cloud is so distant that our fastest spacecraft would take 300 years just to arrive at its inner edge. And when scientists calculated what it would actually take to explore it, they discovered something unsettling. With current technology, it's not just difficult to reach the Oort cloud. It's essentially impossible. Even more disturbing, recent evidence suggests that something is already exploring it, disturbing objects, creating patterns, and possibly observing what enters and exits our solar system. NASA can't reach the Oort cloud, but the question scientists are now asking is, can something else? Dr. Robert Cheng stood before a conference room filled with NASA engineers and planetary scientists, presenting what he knew would be an unpopular conclusion. It was March 2023, and his team had spent 18 months designing a mission concept to explore the Oort cloud, the first serious engineering study of what such a mission would actually require. The numbers are brutal, Dr. Cheng began, pulling up a slide showing trajectory calculations. Voyager 1, our fastest spacecraft in terms of distance from the Sun, is currently traveling at about 17 kilometers per second. At that speed, it will take approximately 300 years to reach the inner edge of the Oort cloud at 2,000 astronomical units. To reach the outer edge at 100,000 AU would take about 15,000 years. He paused to let that sink in. Those are one-way travel times, and Voyager wasn't even designed for the Oort cloud. It's barely functional now, running on power levels so low that most instruments have been shut down. A real Oort cloud mission would need to arrive with enough power to operate instruments, enough fuel to maneuver, and enough communication capability to send data back across those enormous distances. The next slide showed power requirements. This is where it gets worse. At 2,000 AU, solar panels are useless. Sunlight is 4 million times weaker than at Earth. We'd need nuclear power. Specifically, radioisotope thermoelectric generators like Voyager uses. But RTGs decay over time. The plutonium-238 they use has a half-life of 88 years, meaning the power output drops by half every 88 years. A 300-year mission would arrive with less than 10% of its original power. An engineer in the back raised a hand. What about advanced propulsion? Ion drives, solar sails, even nuclear propulsion? Dr. Cheng nodded. We modeled everything. He clicked to the next slide showing propulsion comparisons. Ion drives are efficient, but slow. They'd reduce the travel time to maybe 200 years, still far beyond any reasonable mission lifetime. Solar sails work near the Sun, but provide almost no thrust at Oort cloud distances. Nuclear thermal propulsion could potentially cut the travel time to 100 years. But we've never built an operational system, and the engineering challenges are enormous. He brought up another slide. A conceptual spacecraft design that looked more like a small space station than a probe. This is what we'd actually need. A spacecraft massing several tons, powered by multiple next-generation RTGs that don't exist yet, carrying instruments that can operate autonomously for centuries, and equipped with a communication system powerful enough to send signals across interstellar distances with a transmitter that might weigh hundreds of kilograms. The cost estimates on the next slide drew audible reactions. We're looking at $50 to $100 billion for a single mission. And that's assuming we solve multiple technology problems that currently have no solutions. For comparison, The James Webb Space Telescope cost $10 billion. This would be 5 to 10 times more expensive for a mission that wouldn't return any data for centuries. Dr. Cheng looked around the room. I know this isn't what anyone wanted to hear, but the engineering reality is clear. The Oort cloud is beyond our reach. Not beyond our reach for now, not beyond our reach with current budgets, beyond our reach fundamentally with any technology we can currently envision deploying. The presentation concluded with a stark summary. Recommendation: defer dedicated Oort cloud exploration until breakthrough propulsion technologies become available. Estimated timeline: 50–100 years minimum. But Dr. Patricia Sanders, a mission architect who'd been listening quietly, raised an objection. There's another approach we haven't seriously considered. Instead of one large, expensive spacecraft, what about a swarm? Hundreds or thousands of tiny probes, each barely larger than a smartphone, launched over years and spreading out across multiple trajectories. Individually, they'd be simple. Minimal instruments, basic power, one-way communication. But collectively, they could sample the Oort cloud from many directions. The concept wasn't new. It had been proposed in various forms for decades, but Dr. Sanders had run fresh calculations. CubeSat technology has matured dramatically. We can now build functional spacecraft that weigh kilograms instead of tons. If we mass-produced them and used existing launch vehicles as ride-shares, we could deploy 100 probes for the cost of one traditional mission. Dr. Cheng was skeptical. How do you power them for 300 years? How do they communicate from that distance? And what instruments could you fit on something that small? Dr. Sanders had answers ready. Power. We don't try to last 300 years. We accept that most will die en route. But if even 10% survive to reach the Oort cloud, that's still 10 functioning probes. Communication. We use laser communication instead of radio. It's far more power efficient over long distances. And instruments. We focus on the essentials. A simple camera, a magnetometer, a particle detector. Just enough to tell us what's there. She pulled up her own slides showing mission architecture. We launch them not all at once, but in waves over a decade. Each wave uses slightly improved technology. Some are sent on fast trajectories, maybe reaching the inner Oort cloud in 150 years instead of 300. Others are sent slower, but with more power reserves, designed to last longer once they arrive. It's a distributed approach. We accept high failure rates, but gain through numbers. The room was quiet as engineers absorbed the concept. Finally, Dr. Marcus Torres, a veteran mission designer, spoke up. There's a philosophical problem here. We're designing missions that won't return data for 150 to 300 years. Everyone in this room will be dead. Our children will be dead. Maybe our grandchildren, too. We're asking current taxpayers to fund science that benefits people who haven't been born yet. I'm not sure that's politically viable. Dr. Sanders didn't disagree. You're right. But that's also why we need to start now. If we wait for breakthrough propulsion, we might be waiting forever. Chemical rockets have barely improved since the 1960s. Ion drives are incrementally better. We don't have fusion drives or antimatter engines or any of the exotic propulsion concepts that would make this truly feasible. So we have two choices: start a generational mission now with the technology we have, or accept that the Oort cloud will remain unknown indefinitely. The discussion revealed a deeper problem that had plagued Oort cloud mission planning for years. Humans are terrible at thinking on civilization-scale timescales. A mission measured in centuries requires institutional stability, funding continuity, and cultural commitment that modern societies struggle to maintain. Dr. Elena Rodriguez, a mission operations specialist, raised a practical concern. Even if we launched this swarm, who would be listening for the data 150 years from now? NASA might not exist. The Deep Space Network might be obsolete. The entire geopolitical landscape could be unrecognizable. How do we ensure someone is there to receive the signals? It was a question without a good answer. The Voyager missions, launched in 1977, were barely 50 years old and already struggling with funding for continued operations. Mission teams had retired or died. Institutional knowledge was being lost. Extending that challenge across 3 centuries seemed insurmountable. Yet despite these obstacles, interest in reaching the Oort cloud had intensified in recent years. Not because the engineering had become easier, but because new observations suggested the Oort cloud was more important and more mysterious than anyone had realized. Dr. James Coe, an astronomer at the Harvard-Smithsonian Center for Astrophysics, presented data that had emerged from long-period comet observations. We've been tracking the arrival patterns of comets from the Oort cloud over the past few decades, he explained, and we're seeing something we can't explain. There are statistical clustering, groups of comets arriving from similar regions of the sky within relatively short time windows. He displayed a star map with dots representing comet source directions. If the Oort cloud is a uniform sphere being randomly disturbed by stellar encounters and galactic tides, we should see an even distribution. But we're seeing clumping, about 40% more comets than expected from a specific sector, the direction of the constellation Gemini. Dr. Coe ran simulations to determine what could cause this. A passing star could create temporary clustering as it disturbs a specific region. But our stellar encounter models don't show any significant passes from that direction in the last million years. Galactic tides could create some asymmetry, but not this pronounced. The only explanation that fits is if there's something massive in that sector of the Oort cloud, something with enough gravity to preferentially disturb objects there. The implications were obvious. Planet 9, the hypothetical massive planet in the outer solar system, or something even larger. But without direct observation of the Oort cloud, this remained speculation. This is why we need to go there, Dr. Coe argued. We're seeing effects we can't explain, patterns that suggest structure, and possibly massive objects we haven't detected. The only way to resolve this is direct exploration. But Dr. Hugh Cheng's engineering study had shown that direct exploration was effectively impossible with current technology. This created a frustrating situation. The more scientists learned about the Oort cloud from indirect observations, the more important it became to visit it. Yet the more they understood about the distances involved, the clearer it became that visiting was beyond their capability. Dr. Sanders proposed a compromise. What if we don't try to reach the Oort cloud? What if we just try to reach farther than we've ever gone before? Say, 500 or 1,000 Saturn AU? That's still nowhere near the Oort cloud, but it's several times farther than Voyager. And if we instrument the spacecraft properly, it could study the transition zone, where the sun's influence weakens and interstellar space begins. This intermediate distance mission concept had more realistic requirements. Travel time would be 30 to 50 years instead of 300. Power systems could potentially last that long with current RTG technology. And the scientific value was significant. Studying how the heliosphere extends outward, measuring the density of interstellar particles, and potentially detecting the gravitational influence of distant Oort cloud objects. NASA's interstellar probe concept, under development since 2019, represented exactly this approach. Designed to reach 1,000 AU in approximately 50 years, it would use a close solar gravity assist, swooping near the Sun to gain tremendous velocity from gravitational acceleration, plus advanced ion propulsion. Dr. Breithuarnt Foxter, Rachel and Como, a mission planner on the Interstellar Probe team, explained its capabilities. We won't reach the Oort cloud itself, but we'll venture into its outer influence zone. We'll measure how many interstellar particles are entering the solar system, detect gravitational perturbations from massive objects in the outer reaches, and potentially even observe Oort cloud objects silhouetted against background stars. That last capability intrigued many scientists. Even though the Oort cloud was too dark to see directly, if a probe traveled far enough and looked back toward the Sun, it might detect objects as they passed in front of bright stars, a detection method called occultation. Think of it like watching fireflies at night, Dr. Nkomo said. You can't see them directly when they're not glowing, but you can see them block out stars behind them. If we position our probe in the right geometry and watch enough stars, we might catch Oort cloud objects as they transit across stellar backgrounds. The probability of success was low. Space is vast and Oort cloud objects are sparse, but it was one of the few detection methods that didn't require the objects to emit or reflect light. However, all these concepts faced the same fundamental barrier: funding. The interstellar probe had an estimated cost of $4 to $5 billion, and NASA's planetary science budget was already stretched across multiple missions. Without a dramatic increase in funding or a major breakthrough that would reduce costs, even this intermediate mission remained in the concept phase. Dr. Torres summarized the frustration. We're in a paradoxical situation. The Oort cloud is arguably the least explored region of our immediate cosmic environment. It potentially contains millions of objects, some possibly harboring subsurface oceans or even biology. It's where interstellar and solar materials mix. It might hide Planet 9 or other massive objects, but it's so distant that exploring it is effectively impossible. We're stuck. Then Dr. Nathan Silva, a physicist who'd been quietly listening, offered a different perspective. Maybe we're thinking about this wrong. We're assuming we have to send spacecraft to the Oort cloud. But what if we could bring the Oort cloud to us? Everyone turned to look at him. I'm serious, he continued. The Oort cloud is constantly sending us samples, long-period comets that fall inward and pass through the inner solar system. Instead of spending billions to send a probe out there, why not intercept and study the comets that come to us? Dr. Sanders shook her head. We already study comets. That's how we learned most of what we know about the Oort cloud. Yes, but we study them remotely, with telescopes, Dr. Silva countered. What I'm proposing is intercepting them, sending a spacecraft to rendezvous with a long-period comet, land on it, drill into it, and analyze its interior in detail. We'd be sampling Oort cloud material directly, just at a convenient location much closer to the Sun. The idea had merit. Comets from the Oort cloud regularly passed through the inner solar system. Intercepting one would require far less travel time and energy than reaching the Oort cloud itself, and by drilling into the comet's interior, scientists could access pristine material that hadn't been altered by solar heating or cosmic radiation. The European Space Agency's Rosetta mission had demonstrated this was possible, successfully rendezvousing with and landing on a comet in 2014. But Rosetta had targeted a short-period comet from the Kuiper Belt. Intercepting a long-period comet from the Oort cloud presented different challenges. Dr. Ko pulled up orbital data. Long-period comets move fast, much faster than short-period comets. Rosetta took 10 years to slowly match orbits with its target. To intercept an Oort cloud comet we'd need to launch on a trajectory that intersects the comet's path, which means a high-speed flyby rather than a gentle rendezvous. Landing would be difficult, possibly impossible. Then we don't land, Dr. Silva suggested. We do a close flyby with instruments designed for sampling. Cameras, spectrometers, a mass spectrometer that can analyze particles in the comet's coma, maybe even a penetrator, a small impactor that hits the comet and throws up debris for the spacecraft to fly through and analyze. This concept, comet flyby missions targeting Oort cloud objects, was more feasible than trying to reach the cloud itself. Travel times would be measured in years, not centuries. Costs would be comparable to other planetary missions, and the science return would be immediate. Dr. Cheng saw the appeal. This is actually doable. We could design a mission around targeting the next bright long-period comet discovered, keep the spacecraft ready to launch on short notice, and when a suitable target appears, we go. The discussion shifted to target selection. Which Oort cloud comets would make the best targets? The ideal candidate would be large, bright, and on a trajectory that allowed for interception with reasonable delta-V requirements. Dr. Ko had been maintaining a database of potential targets. There are typically 1 or 2 good candidates per decade, he said. Comets bright enough to study in detail, but not so close to the Sun that they've been heavily altered by heating. The next really good opportunity might be Comet C2024G4, expected to pass through the inner solar system in late 2027. If we started designing a mission now, we could potentially be ready to launch by 2026. The timeline was tight but feasible. The room's energy shifted from frustration to possibility. This was something they could actually do, not in 300 years, but within the current decade. Dr. Pofor Sanders began sketching mission architecture. Small spacecraft, maybe 500 kilograms, solar-powered since we're in the inner solar system, a suite of remote sensing instruments plus a sampling mechanism. Launch on a medium-lift rocket, perform 1 Earth gravity assist to match the comet's trajectory, flyby at close range, maybe 100 kilometers, and transmit data in real time as we pass. The estimated cost came to roughly $800 million, expensive, but within the range of NASA's Discovery-class missions. It would require approval, funding, and several years of development, but it was achievable with existing technology and current budgets. Dr. Cheng found himself cautiously optimistic. This doesn't solve the problem of actually exploring the Oort cloud in situ. We'd still be studying it secondhand, through samples that fell inward. But it's something we can do now, with real scientific return, while we wait for the propulsion breakthroughs needed for true Oort cloud exploration. The meeting concluded with a consensus. Propose a comet intercept mission targeting an Oort cloud object, while continuing to develop concepts for future long-duration missions as enabling technologies matured. But as the room emptied, Dr. Torres pulled Dr. Silva aside. You know what bothers me about all of this? We're treating the Oort cloud like it's just sitting there, waiting for us to eventually reach it. But what if it's not? What if something's already there? Dr. Silva frowned. What do you mean? The clustering Dr. Ko showed. Comets arriving preferentially from one direction. The strange chemistry Dr. Foster's team has been finding. The gaps in comet arrivals that Dr. Bao Chen documented. What if all of this points to activity in the Oort cloud? Not natural perturbations, but something intentional? You're suggesting intelligence? Dr. Silva asked carefully. I'm suggesting we might not be the only ones interested in the Oort cloud, Dr. Torres replied. If there are interstellar probes from other civilizations exploring the galaxy, The Oort cloud would be the perfect place to station observers, far from the sun's heat and radiation, but gravitationally bound to the solar system. They could watch us from there for millions of years, and we'd never know. Dr. Silva wanted to dismiss this as speculation, but he couldn't entirely. The clustering, the anomalies, the unexplained patterns, they did suggest something more than random chance. If you're right, Dr. Silva said slowly, then maybe the real question isn't how we reach the Oort cloud. It's what we do when what's already there decides to reach us. The two scientists stood in the empty conference room, contemplating a boundary that humanity couldn't cross, wondering what might be looking back from the other side. Thanks for watching another episode. While you're still here, make sure to click the video on your screen for more quality content.